Hello everybody. Today we are going to be going over continuous functions, or in general just continuity. So over the past few videos we've looked at functions where we could evaluate the limits just by evaluating the function at the point in question. So it'll be the limit of, as x approaches a, of f of x. And basically the questions that we had gone over targeted continuous functions. So what does it actually mean for a function to be continuous? We're going to be going over that today, and we're going to try to cement into our heads what it means for a continuous function to exist. So we'll write down our first definition. We'll say a function f of x is said to be continuous at x equals a if we'll say the limit as x approaches a of f of x is equal to f of a. So a function is said to be continuous on interval a comma b if continuous at all points in this interval. So that's basically what it means for it to be continuous. And this is also assuming both f of a and the limit as x approaches a for f of x, they both exist. If one of these don't exist, then the entire function is not continuous. So we could add this to our definition. We'll say say if f of x if f of x is continuous at x equals a, then we'll say the limit as x approaches a of f of x is equal to f of a, just like we said before, but also the limit as x approaches a from the left or the right hand side is equal to f of a. And we'll say the same for here as well. So if f of x is continuous at x equals a, then all of this will be true. The limit as x approaches a of f of x is equal to f of a. The limit of f of x as x approaches a from the left-hand side is f of a, and the limit as x approaches a from the right-hand side for f of x is equal to f of a as well. So although this is a lot of definitions that I'm throwing at you, let's take a look at what it means, I guess, like on a graph for a function to be continuous, because that should give you a much better understanding of what it means for a function to be continuous. Now, say this represents f of x, or if this graph represents f of x, is f of x continuous at x equals -2, x equals 0, and x equals 3? take a second to think about it based off what we learned before and try and answer for these three individual values. Okay, now let's start with our first x equals -2. So we'll ask the limit, we'll write down the limit as x approaches -2 of f of x. It doesn't exist, as we can see from here. As x approaches -2, it goes towards both the -2 and +2. So we say this does not exist. So the first x is not continuous, or f of x is not continuous at x equals -2. So I guess we'll mark that as not continuous. And x equals 0, we see as x approaches 0. So we'll say the limit as x approaches 0 of f of x is going to be, well, a value right here. There are no multiple points at this point, and it is the same from both the left side and the right side. So we could use that logic, and we could just say, oh, well, the limit as x approaches 0 of f of x is 1. So we'll mark this down as good. And we'll say 1. Say, we'll say, I guess, f of 0 is equal to 1. And now let's take a look at x equals 3. So as x approaches, we'll say the limit as x approaches 3 of f of x, what is that going to be equal to? We see from both the left-hand side and the right-hand side that it does approach, I guess, 0, but we see that this is an open circle, and thus it is not defined. So we would automatically say that they both approach -2 right here. But this is not continuous due to having both a value that does not exist and a value that does exist. So we would say this limit would be, so let's say f of 3 is equal to negative, I guess, 2 in this case. Let's rewrite that. 2, geez. There you go. -2, but not continuous due to hole. And this is actually going to segue us into our next, I guess, example. So we see here that this last point at x equals 3, we're not able to say it's continuous due to the hole that exists right here. We're going to go over another example that'll help us understand that point. So I'm going to ask, is the following function, let's say, continuous till infinity? And we'll say h of t is equal to 4t plus 10 divided by t squared minus 2t minus 15. And if so, which points are discontinuous? So try and solve this, and remember that, of course, this isn't going to be continuous from negative infinity till infinity, just due to the fact that there could possibly be values that we can't use um, in the denominator, which will make it, I guess, discontinuous at that given point. So try and find the zeros that basically give you the points which are discontinuous. All right, so let's go over it right now. So we already know that we need to take away the denominator in order to find which points it does not exist at. So we'll take this t squared minus 2t minus 15, and we can turn that into t minus 5 and t plus 3. Let's erase this. So we see that our zeros are here right now, right? So I hope this could help to cement, if t is 5, wait, let me change my brush size. If t is either 5 or negative 3, then this entire point at a given t is basically not, it is basically undefined. It does not exist. And because it does not exist, it is not continuous at that point. So we would say it is not continuous at t equals 5 and negative 3. So now that we've gone over this, we can create a new addition to our definitions. We'll say if f of x is, well, actually, let me decrease my brush size. F of x is continuous at x equals b, and the limit as x approaches a of g of x is equal to b, then we can say the limit as x approaches a of f of g of x, which would technically be f of g. Well, I mean, either or, it's the same. That would be equal to f of the limit as x approaches a g of x. And basically, we've actually seen this rule in a previous video before. It was for a log function, I believe. But we can basically use this for, I guess, say like a messy limit that might look intimidating. Like, for example, we'll say, find the following. We'll say the limit as x approaches 0 of e of to the sine of x. Now, using the rule we just learned before, we could just say e we'll make this equal to e to the limit as x approaches 0. Well, I mean, we have to say it here. Limit as x approaches 0 of sine of x. And we know the limit as x approaches 0 of sine of x is just going to be 0. So that's just going to be equal to e to the 0, which is going to be equal to 1. So yeah, we could use that rule we just gone over to solve, I guess, messy limits like this one right here. Another consequence, or not consequence, but another, I guess, byproduct of continuity is actually going to be a specific theorem. And we are going to call this theorem intermediate value. Let me just spell that. The intermediate value theorem, which basically says, see here, suppose is continuous A to B, I guess we'll say blue for M. Present I guess any number between and f of b. Then there exists a number c such that, and we should probably make some room for this. Oops. Let's see here. Just move this a bit out. This is a bit messy, but forgive me. A is less than C, which is less than B, and 2, f of C is equal to M. So the intermediate value theorem. Suppose f of x is continuous from A to B, and let M represent any number between f of A and f of B. Then there exists a number C such that A is less than C, which is less than B. And f of C is going to be equal to M. All this really means is that a continuous function will take on all values between f of A and f of B. And I guess let's create Let's show this but in graph form. So we can see from this graph here and this theorem I found online. Um, suppose that f is continuous on the closed interval from a to b, and let m, well, it said n before, but it said let m be any number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c in a comma b such that f of c is equal m. So basically, this is just saying that you can basically, there exists a number between a and b, that's basically, um, I guess there will be like values in between these 2 points, um, and it will take on all values. It's basically saying it's going to be continuous if it's continuous from this given interval. So that's all it is for intermediate value theorem. It's not very, I mean, it's pretty, it's fundamental, but it's like pretty, it's literally just common sense. Like if a function is continuous, it's like there's not going to be like points on this closed interval where it's continuous, where there are um undefined points or whatnot. Um there will exist a number c in a comma b such that f of c is equal to any number between f of a and f of b. That's literally all that's saying. It's just kind of common sense when it comes to it. But yeah. So this is going to be it for continuity for this video. And yeah, we're going to be continuing Calc 1 and the leetcode stuff. So yeah.